Hey everyone, how goes it? And welcome back to Computer Science 146. Today, we're going to do some programming review. More specifically, we're going to do some procedural programming. So we're not going to focus heavily on code organization like using methods or objects and that such. We're just going to focus on straight down, one at a time, statement by statement kind of programming. Foundationally, we need to start with some basic computation. In the previous lecture, it was brought up that the brain of the system is your central processing unit, your CPU, but also the memory is where the information of the program is stored. Now, the CPU can utilize the memory and store information about the program. Now, variables provide a means to do this. Variables are effectively boxes. They are containers for that kind of data. And the values in a variable are allowed to be changed. They could be modified or mutated. The first thing that we need to do to use variables is we need to declare them. Now, this creates that space in memory to store that information. And the way that we create them is by using what's called a type, followed by an identifier. Now, just like a programming language is very similar to a natural language, think of it this way. You are communicating with the system. You are saying, reserve some space in memory for this type called this identifier. Going into a little more detail, as we said before, when we declare a variable, we have to provide a type and an identifier. So looking more closely at the type element of this corresponds to the number of bytes in memory that we're asking for. Now, programming languages could either be strongly or loosely typed. Java is a strongly typed language, indicating that each one of the types correspond to a specific amount in memory, how many bytes that we have to reserve. Now, other languages may be considered loosely typed where they have one universal type that is all of the same size. Going further with types, you can break them down into two versions, primitive types and object types. Now, primitive types, you can think of those as simply it's just a number. That's all that is stored in a primitive type value. Object types are a little more advanced, but you can break them down into two essential elements. The object itself references some kind of contents found somewhere else in memory. Now, in these classes, over to the side here are very common primitive types, and what is bolded is the different versions that we're going to be using more commonly in this class. Something to keep in mind, once again, that the type corresponds to the amount in memory that we are declaring, that we are saying reserve this much space. For instance, an integer is 4 bytes in memory. This means that it stores at most 2 to the power of 32. Why? There's 8 bits in a byte, 4 times 8 is 32, 2 to the power of 32 possible numbers in an integer. Now, in addition to that, integers are whole numbers. They have no fractional values. Even if you divide them, like for instance, if you took the integer 1 and divided it by 2, you end up with the value 0. Integers do not round in any sort of way. Anything that happens after that decimal point is completely removed. Integers are great for whole number values, but that's not the entire story. If we require decimal values, then what might be more appropriate is another type called double. Double is short for double precision floating point number, and this allows programmers to use those decimal points in a more precise way. By giving it twice the number of bytes of a float or a normal floating point number, you can have large form numbers. Just like the integer had the range from 2 to the power of 32, think of it this way. 8 times 8 is 64, so this has 2 to the power of 64 possible numbers. Now, a Boolean is 1 bit. It's either true or false. Now, characters are 2 bytes in memory, but do keep in mind, it's a primitive type, so all characters are simply numeric values. But the system knows to represent them lexically, so in other words, represent them as letters. To give a slight demonstration of this, if we had the following code where we're declaring 3 types of variables, an integer, whole number, double precision floating point number, and a character called O, you can look to the side here and see what happens in memory. Now, the memory in this case is broken down into its identifier, its contents or the values, and the byte address. Inside of memory, we have to have the address to store values. So for instance, if we start out with this first step where we are declaring an integer value called I, what effectively happens is this. The system will look through and try to find a place in memory that can accommodate 4 bytes because it's an integer. Let's just say for argument's sake that byte address 28 is a space in memory. So what it does is it creates that identifier, I, and it also sets the value to 0. The reason why it does that is because Java assumes default values for everything. That's not necessarily true for every programming language, but it is for Java. Going to the next statement, now the computer has to procedurally create a double named J. So it creates the identifier, assigns the contents to the default value, 0, but pay very close attention that this byte address starts at 32. Now going from I, an integer is 4 bytes in memory, and that started at memory address 28. 4 plus 28 is 32, so this is where this information would start. Now when it reaches the character, it does the same thing, where it basically creates 2 bytes in memory and then assigns a default value. Now you may notice this very strange looking default value for a character right here. When a character is declared, it assumes the default value, and in this case, this is the character value of nothing. We sometimes call that value null. Now just like before, this character takes up 2 bytes in memory, so the next possible variable that could be declared would have to start at byte address 42. Always keep in mind that the types in a strongly typed language like Java indicate the amount of memory that we are reserving to save that information. Now when declaring variables, there was 2 parts. We focused on types first, but also the naming of variables, their identifiers, have some rules as well. We use the identifiers to both retrieve and store the information. And a lot of programming languages, Java included, are case sensitive when it comes to variable names. In other words, if we were to declare int test, and int test, all 3 of those would be different identifiers. It is really good programming practice to use camel casing whenever you are declaring variables. So basically the idea is you lowercase the first letter in a word, and then after that word you uppercase the first letter in every subsequent word in the identifier. So if you notice over here, where we have large and then values, you lowercase the L, but you uppercase the V. And same thing here, in class, you lowercase the I, but uppercase the C. Using this technique makes your code more readable, and that is a very good programming practice. It allows you to detect errors if they exist inside of your system a little faster, and it also allows for better collaboration with other programmers. In addition, identifiers have some specific rules. First of all, they cannot start with a digit. You cannot have spaces in an identifier, which facilitates the use of the camel casing, and also an identifier cannot match a reserved word. Along with that, identifiers should absolutely avoid using special characters and confusing names. You want this code to not only be understood by the computer, but by yourself and other programmers as well. Give variables meaningful names. So over to the side here, there are a couple of bad examples that will end up with syntax errors. And the first one, this one starts with a digit. This would be a syntax error. This one has a space in the identifier, so it's going to think that you were trying to declare double big and then just put some stuff after it. Now in this case, this Boolean is using a reserved word, and we know in Java, public class is the first thing we use to organize our code, followed by methods. So by trying to declare Boolean class, this would also be a syntax error. Declaring variables allows us to reserve space in memory to store information and give it a meaningful name or identifier. But that's not the entire story. In order to utilize those parts of memory, we have to use a special symbol called the assignment operator. Now, the equal symbol in Java is the assignment operator, and this works very different from the mathematical equal symbol. So in math, the equal symbol indicates that everything on the left-hand and the right-hand side are equal. 2 plus 2 is equal to 4. In programming, you are storing the information found on the right-hand side into the container on the left-hand side. Now, assignments are only valid if the types match or they are compatible. For primitive types, for instance, you have to think about the amount in memory. So, for instance, an integer is 4 bytes in memory, but a double is 8 bytes in memory. You can store 4 bytes into an 8-byte container. But going the other way around, trying to store 8 bytes into 4, you can't do that without a technique called typecasting. Now, keeping in mind, just like with integer values, typecasting does not round. It cuts off everything past that decimal value. So if you think about speaking to the computer, what you're effectively saying is store this value into this container. Now, furthermore, with the examples, you can see how these assignments work. The integer I is assigned to 0, assuming that it was declared given the previous code. Now, you have the value double j, which is assigned to 22.3, and the value character O is assigned to h. Now notice, characters are denoted by the single quotations. Strings are double quotations. And also right here, what we need to do is we're trying to store the value of j, which is a double. It has 8 bytes in memory, into a container, which is an integer, 4 bytes in memory. We have to typecast this, which basically converts this double into an integer, which effectively just takes this part right here, everything before the decimal point. So when you typecast j into I, the value is 22. As programmers, we're not lazy, we're efficient. We create shorthands more often than not for very common operations, and it is very possible to do both declaring a variable and assigning it at the same time. But do remember that there are different parts to this. So in our example, if we start right here, we have this integer value I. This part here is the declaration of I, so basically saying reserve 4 bytes in memory and create the default value of 0. Now the next part here is the initialization. This is taking the right-hand side value and storing it into the container called I. Nothing really exciting happens here. 0 just remains 0. Now once again, we're going to declare a double j. So when it declares it, it reserves 8 bytes in memory and names it j. After that, it assigns the value 22.3 to the contents of j. Same thing here for character O. We reserve 2 bytes in memory and store the character h inside of it. Now once we get to here, we are going to reassign the value of I. Notice that we are not using the type. The type is only used for the declaration. If we were to use the type again, in other words, if this said int I is equal to typecast int j, then you would get a syntax error saying that you have a duplicate identifier, and you cannot have duplicate identifiers. So what happens here is after we have reserved the space, we are going to reuse the identifier I. We're going to typecast j, which contents contain 22.3. By typecasting, we cut off everything past that decimal point and reassign the value to 22. Now, along with variables, we have these other containers called constants. So variables can change in memory, but constants are created once and once only. Using constants is a great technique to avoid what's called magic numbers. Now, magic numbers basically just kind of come out of nowhere. They just appear magically from nothing. Creating a constant gives that value some sort of context. So it is always a good idea when you recognize a value will never change, just go ahead and make that a constant. It's also good programming practice to go ahead and make all the constant scope public, make its memory static, in other words, it's statically defined, and also capitalize all the characters in its identifier. So you can see over here, the syntax for Java, for instance, is you would create, again, outside of a method, but still inside of a class, public, which makes it accessible, static, meaning that it is statically defined once in memory, final, meaning that it is a constant, and then you follow with the type, identifier, and the assignment of the value. Now that we can reserve space for information and we can store that information, let's start doing some basic computation using some math operators. The way to think about this is math operations happen on the right-hand side. All of that information is computed and then stored in the left-hand side. So the order of operations, so please excuse my dear Aunt Sally, is still in effect inside of programming. Now the basic math operations are like addition, subtraction, multiplication, and division, and I'm not going to go into a lot of detail about that. However, there's a special kind of operator that we call the mod operator that we use a good bit in computing. Now this returns the remainder after some form of division. For example, if we basically did 15 mod 2, the result is 1. And that's simply because 2 goes into 15 7 times with a remainder of 1. Now, math operators are not just applicable to variables. You can also use them with constants as long as they're utilizing other constants. In addition to those basic math operators, we also have shorthands for basically applying some sort of operator to some sort of value. So these are basically thought of as compute, then assign operators. So the way that you can think about this, you have the different versions, plus equals, minus equals, times equals, divide equals, and even mod equals. So if I have this example here, I is equal to I plus 1, this is equivalent to I plus equals 1, and an even more special case, I plus plus. Just like I said before, there are some special versions where plus plus increases whatever that value is by 1, and minus minus decreases that value by 1. So over here, some of the examples would be if we had the value I here, and assuming that it was assigned to 32, if we do I plus equals, in other words, 32 plus 128, and assign that back to I, now I is 160. Similarly, if j was assigned to the value of 28, and we do j mod equals 2, 2 goes into 28 14 times, with no remainder, so the value would be assigned to 0. Again, the compute and assign operators are just a shorthand for something that we commonly use. Now, if you don't like using those, then simply enough, you can just use this version without any issue. The abstract model that we gave in a previous lecture indicated that we have some sort of input being passed into the computer, it computes something, and then creates some kind of output. Now, the basic version of output in Java utilizes what's called system.out.println. And effectively what this does is it prints to the standard system out, the console. So anything that is inside the parenthesis here is printed to the console. So for example, if we declare int I, assign it the value 22, and we call system.out.println I, the console will print out 22. Now, input is a little more tricky. What I heavily recommend is use the type scanner to read information from the console. Now, before you can use this type scanner, you have to import the package java util. So in other words, before the class, you have to put import java.util.scanner. After that, create an instance of that type scanner that scans the standard system input. So if you basically declare type scanner with the identifier keyboard, then construct it passing system.in, this will read anything that is entered into the console. The scanner is an object type, and object types indicate that you have some sort of reference, some sort of contents, and also object types combine together information with functionality. The functionality are called methods, and there are some useful methods that you should consider using when you're reading from the console. For instance, the method next returns a string that goes all the way up until it reaches some kind of space or even inline. Next line reads all of the input until it gets to an inline. Next int looks for the first integer value, and also next double looks for the first double value. Scanners are not just useful for reading the console. You can use a scanner to scan through strings, through files, network traffic, all that kind of stuff. Now, if we look over here, we can see this example where we start out by declaring type scanner identifier keyboard. Then we construct this keyboard passing in system.in, so it's going to read from the console. Now, what we do here, string name, we assign that to keyboard.nextLine. If we look down here, we can assume that this value was entered in by the user, which means this was captured and stored inside of the value name. Then here, int I is equal to keyboard.nextInt. So if we entered this integer value, 64, now I becomes 64. Notice very specifically here, I heavily recommend, if you're going to call nextInt or nextDouble, go ahead and call keyboard.nextLine so you don't accidentally run into a strange kind of bug. Now finally, we use the output system.out.println, and basically we take the name, that was that type string, and we concatenate it with a space, concatenate that with the value of I, which was 64, concatenate that with a space, and then concatenate that with the value of j, which was 3.14. When we print that out all together, this is what we get. While we've been focusing on primitive types, there are some very common object types that we need to discuss. One of the most important ones is the string. Now yes, this is an object type, which means you have a reference that refers to the contents somewhere else in memory. The best way to think of a string is it's simply an array of characters. We're going to get to arrays a little bit later on, but effectively what that is it's a collection of those values. It's a collection of characters. Whenever we've been using strings, we use the double quotes to denote them. And once again, characters are denoted by single quotes. Now the plus operator with a string concatenates a value with that string. It doesn't work like the mathematical plus symbol. You're not adding together these letters. What you're doing is appending them to the end of the string. Now, as strings are object types, they have a lot of methods that are built into them. So some of the most useful ones would be character at some kind of index, substring from some start index all the way to the end of the string, substring with a start index and an end index. And now keep in mind, in this version of substring, the start index is inclusive. It includes that value, and the end index is exclusive. It does not include that value. To uppercase, to lowercase, and also split, which we'll get to in a little bit later. Now if we take a look at this example, if we declare this string called str and assign it ABCDEFG, if we call system.out.println string car at 0, now with arrays, the first valid index into an array is 0. So basically what this says is print out the first character in this string. And as you can see here, if we think of this as index 0, 1, 2, 3, 4, 5, and 6, then it simply prints out A. Now, if we create a new version of this string and we call substring going from index 2 to index 5, remember, this 2 is inclusive, this 5 is exclusive. So 0, 1, 2 includes C, 3, 4, but not 5. and this is why it prints out C, D, and E. I highly recommend to look through all of the methods that are built into strings, because this can be very useful in solving many of our problems. So if we want to look further into strings and how this works in memory, again, this is an object type, where we separate the variable which contains a reference to the contents found in memory. Now, if we have the string ABCD, the first thing that we do is we initialize the value of that string. So, as you can see here, the identifier is str. The contents currently, because we haven't assigned it, is this special thing called null. Null is a memory address, and the identifiers for objects contain memory addresses. The null memory address indicates that this object has not been constructed. We have reserved space potentially, but it doesn't exist inside of memory. We have no reference to it. Now, when we get to this part right here, what we first need to do is reserve inside of memory this array of characters of size 4. If you notice, this byte address is just arbitrarily picked. Now, once again, characters are 2 bytes in memory. Arrays are contiguous blocks in memory, and if you notice, every subsequent memory address increases by 2 bytes. String's default value is this string version of null, but once we assign each of these individually, it becomes ABCD. However, if you notice, the identifier still says null, because the last step after we have created that instance of a string is now we assign str the value of the byte address. And the way you could think about this is str simply points to the contents of the string somewhere in memory. Now that we've discussed some basic computation, let's go a little bit further and start discussing flow control. Flow control indicates how the program is going to function. And there's some cases where maybe you want to run some code sometimes, and there's some cases where you might need to loop some code sometimes. One of the first elements of flow control is what's called a branching statement. Now, an if statement is a version of a branching statement. Now, in the if statement, if the Boolean expression is true, then the body of the if is run. Now, if the Boolean expression is false, we ignore everything in this body. Now, as described before, the open and closed curly brace indicates the body of something, and so this is the body of the if statement. I highly recommend to go ahead and put the curly braces to denote the body of these different statements. It just makes it a little easier to debug. Now, also notice that after the parenthesis, there is no semicolon here. Please do not put a semicolon right here, or basically it's always going to run the body of this if statement. Now, as this is a language, if you are thinking that you're speaking to the computer, think about phrasing it this way. If this is true, then do this. Now, in addition to the if statement, there is something called the else statement. Now, an else statement does require an if. You can have an if without an else, but you can't have an else without an if. And basically, what the else takes care of is specifically, if whatever the Boolean expression was false, then it does this instead. So in this case, if the value stored in A is equal to B, then we print out A is equal to B. But if this is false, this is ignored, and then this happens. In addition to the if and the else, there's a shorthand called an else if. Now, what this indicates is it is an if statement in the body of an else statement that is tied to another if statement. Now, looking at this in a little more detail, you can basically say that this is equivalent to that, because as you can see, we have this else if here that corresponds to an if statement in the else block of another if statement. But we shorthand this to make it a little more readable. A common mistake that I see with early programmers is assuming that these are equivalent, and they absolutely are not. Let's take, for example, this one. If the value here is true, Remember, this is the else part of it. So you don't run the else if this is true. So effectively, if this Boolean expression is true, you run statement 1 and immediately jump out. However, over here, if this Boolean expression is true, this statement runs, but then it doesn't jump out of here, it moves to the next if. And then the next if, and then this if and else are the only ones that are tied together. Always keep in mind, an else if indicates that it is an if statement in the else block of another if statement. This also implies that the else if, in order for it to run, it depends on the previous if statement being false. There are some cases where branching statements are dependent on one another, and other cases where they are independent from one another. Now, with all the talk about branching statements, we keep bringing up Boolean expressions. Now, what those are is some sort of way to render a true and a false value. And there's a lot of common Boolean operators that we use. For instance, the 2 equals is equal to, and now this one is like the mathematical operator equals. Now remember, the assignment operator is a single equals, which means store the right-hand side into the left-hand side. But this equal to indicates that both the left-hand side is equal to the right-hand side. In addition to that, we also have not equals, strictly less than, strictly greater than, less than or equal to, and greater than or equal to. So in this example down here, we can see that we have declared this Boolean a, this 1 bit, and we assign that to this Boolean expression, 12 is greater than 3. We know that this is true, so a is assigned to the value true. Now if a is true, which we can indicate it here, or we can be doubly sure and say a double equals true, both of these are equivalent, then we print out here. You can also combine Boolean expressions together using a couple of very common operators. The first one is the AND operator, which indicates both expressions have to be true in order for the compound expression to be true. We also have the OR operator, that is the opposite of the AND. So in this case, only one element has to be true in order for it to yield true. Now the exclamation point isn't like AND or, but it does negate the value that was already stored there. Now, this is a very useful truth table right here, and assuming that we had 2 variables, a and b. If a and b are both true, as you can see, a and b is true, a or b is also true. Now, if the value of a is true, but the value of b is false, a and b would be false, however, a or b would be true. Now, notice here, the only time the or could be false is if both a and b were false. Now looking over here, we have this Boolean a, which is assigned to 2 is not equal to 0. We know that's true. And 12 is greater than 3. We also know that's true. Because this side is true and this side is true, a is assigned the value of true, so it prints out here. Along with that, Java takes the stance on what's called lazy evaluation or short circuit evaluation. In other words, if this first expression was false, it doesn't even look at the second part right here, because it knows that in order for an AND to be true, every element must be true. You can utilize the short circuit nature in order to improve some programming. Now, the other part of flow control is called loops. And basically the idea is you're running a block of code some number of times over and over again. And the block of code is indicated by the body of the loop. One very common loop is called the while loop, and these are check then iterate types of loops. So in other words, while this Boolean expression is true, you run the body. However, if this Boolean expression is false from the beginning, the body is completely ignored. So the body of a while loop may run 0 to many times. While loops are excellent when you're unsure of the number of times that this loop body needs to be run. And a good way to think about this as you're speaking, communicating with the computer, is you're saying, while this is true, keep doing this. Or another way to look at it is until this is false, keep doing this. Do-while loops are another version. Now, these are iterate then check because unlike a while loop, the body of the do-while loop runs at least once. Now, these are also great when you're unsure of how many times the loop body has to run, but you know for sure that the body has to run at least once. One little trick with the do-while loop, now this is not the same with a while loop, an if statement, else if, or anything like that, because if you notice, there's a semicolon right here. Don't forget this semicolon or else you'll get a syntax error on your do-while loops. And if you're communicating with the machine, do this while this is true. The last kind of loop I'm going to go over is called a for loop. Now, these are counting loops. The body of the loop runs some number of times. And effectively, this is a shorthand version of a very common while loop. Now, if you notice the syntax over here, it's a little more advanced than just having a Boolean expression in between the parentheses. You have this first section where you initialize a counter. For loops are counting loops, so we have to have a means to count. The Boolean expression is just like the while loop. So we start this counter here, and we keep running this until this is false. Now, you have the updating of the counter, which this seems a little weird because this happens after the body of the loop has been run. So in fact, the way that a for loop works is you initialize the counter first and once only. You check the Boolean expression. You then run the body of the loop and update the counter. Then you check the Boolean expression, run the body of the loop, update the counter, and this is how it loops. Communicating with the system, you are saying, for this starts here and ends here, do this that many times. So in this case, we have for int I is equal to 0. We declare the variable I, assign it to the value of 0. While I is less than 10, I plus plus, increase it by 1. So starting here, we declare it. 0 is less than 10, so we print out 0. Then we increase I by 1, making it 1. 1 is less than 10, print out 1. Add 1 to it. Now we're at 2. 2 is less than 10, print out 2. 3 is less than 10, print out 3. 4, 5, 6, 7, 8, 9. 9 is less than 10, print out 9. 10 is not less than 10, stop. The last thing I'm going to go over in regards to procedural programming is one of the foundational elements of this class. It is called arrays. An array is a collection. It is a data structure of items of the same type. Now, the way to think about this is it is a fixed, contiguous block in memory. This indicates that you cannot resize an array in memory. So this means that you need to know the size of the array before it is created. Let me also mention that resizing is not the same thing as creating a larger array and then moving all the information from one array to another. That is not the same thing. Now, Java is a language that considers arrays as objects, much like strings. You have a separated reference and its contents. But also objects have data and functionality associated with it. One very important built-in property to arrays is the length. How many items are in this array? Whenever arrays are constructed, all of the items are assumed to be assigned to some sort of default value. Now, this is true in Java, but it's not necessarily true in other languages. It is a good programming tip to go ahead and once you construct the array, assign all the values to some sort of default value on your own. In order to access and modify elements of an array, we have to use a thing called an index. Now, the valid indices start from index 0 and go until the array's length minus 1. So in other words, if an array had 10 elements, the valid indices is 0 to 9. Now, as a for loop is a counting loop, the for loop and arrays go hand in hand together. If we notice over here, the way that we declare and construct an array is we start off with the type and then these square brackets. This indicates that this is an array of this type. We then give it an identifier, and then we use the word new to construct this type of this many elements. Whenever we need to access elements in this array, we use its identifier followed by the square brackets and the index of the item that we want to retrieve. Now, if we were going to use the same idea to access and then modify the value, what we do is we use the array's identifier, the square brackets, the index of the item that we want to reassign, and then assign it to this value. So in this case, what we have created here is this integer array, which we called I, and we've constructed it with 5 elements. We then index into index 2, which is the third element, 0, 1, 2, and assign that to the value 22. So then, if we system.out println I at index 2, it simply prints out the value 22. Going into a more detailed example, let's follow this and what it looks like in memory. The first thing here, what we do is we declare the instance of this variable. So it creates the identifier A, and then it assigns its contents to null. Once again, in Java treats arrays like objects, so you separate the memory reference from its contents. Now we construct the new instance of this array using the 5 items. And what you could see right here is we have constructed each element of this array. In other words, 5 different integers here, and assign the default values of 0. Arrays are contiguous blocks in memory. The first index arbitrarily was picked at 72, but every other index after that increases by 4, the size of an integer. Now, once that's been constructed, the value that is contained in the identifier A is not the array, but the reference to the array, so it points right there. Now we get into this for loop, and once again, we have to declare the variable I here, which is assigned to 0. Now, while I is less than the length, and the length that we have here is 5, so 0 is less than 5, then we assign the value. A at index 0 is equal to 0 times 2, which is 0. Another way to think about this is whenever you are indexing into an array, what you have here is the type. Now, as this is an integer, this is 4 bytes in memory. You take the 4 bytes and multiply it by the index inside of here and add it to the start address. In this case, the start address is 72. The amount of bytes is 4. 4 times 0 is 0 plus 72, so assign the value at 72, value of 0. Now we increase the value of I by 1, and then we check it again. 1 is less than 5, so we run the body of the loop. Now in this case, we're doing A at index 1. So this means the size of an integer is 4 bytes. 4 times 1 is 4, plus 72, which indicates byte address 76. So store the value 1 times 2, 2, into memory address 76. Increase I by 1. And this procedure keeps happening until we're at the end. And as you can see here, we've assigned all the values into this array 0, 2, 4, 6, 8. We went over a lot of information today, and this is the basics of procedural programming. And with all that being said, I'll see you next time.